In reverse osmosis, we use the Silt Density Index, or SDI, to measure the exact concentration of suspended solids and colloidal matter entering the feed water. It's an industry-standard calculation derived by pushing water through a 0.45 micron absolute filter at a constant pressure. There is a persistent assumption on the plant floor regarding this metric. Operators often view an elevated SDI reading of 4 or 5 as a universal inconvenience, a sign that they will simply have to run cleaning cycles more frequently, regardless of the plant they are operating. But that assumption falls apart when we track high SDI water into two different environments, a Brackish Water RO system and a Seawater RO system. The identical feed water behaves entirely differently depending on which system it enters. The measurement standard for SDI remains static across the industry. The physical penalty for a high SDI, however, is strictly dictated by the system's thermodynamic environment. SDI quantifies the failure potential. Under high pressure, the index tracks the transition from a manageable operational nuisance to a catastrophic structural threat. Two parallel RO skids, Plant A for brackish water, Plant B for seawater, receive an identical 4.5 SDI feed. Plant A shows a steady permeate decline and mild pressure rise, remaining operational. Plant B's differential pressure graph aggressively spikes, causing complete system failure. The data reveals two distinct outcomes. One manages a gradual performance dip, the other suffers total structural shutdown from the exact same water. To understand why a membrane fails, we have to look past the SDI number displayed on the control panel. We need to examine the fluid mechanics occurring inside the pressure vessel. The primary variable dictating the engineering of any RO plant is total dissolved solids, or TDS. Brackish water contains up to 10,000 ppm of dissolved solids, meaning low osmotic pressure. Seawater starts at 35,000 ppm, creating a high barrier. Brackish systems require 15 to 25 bar. Seawater systems must generate a massive 60 to 80 bar of downward force. This differential is the dividing line. The shear forward thrust generated by an 80 bar pump strictly determines how suspended colloidal matter behaves when it makes physical contact with the membrane. Seawater desalination requires an extreme physical realm, where massive forward thrust turns standard suspended solids into microscopic projectiles. When high SDI water enters the brackish system at 20 bar, the fluid mechanics are relatively forgiving. On this thin film composite layer, colloidal particles arrive at moderate velocity and stack onto the surface, creating a porous cake formation. This structure remains permeable. High pH cleaning chemicals can penetrate the cake and dissolve the fallants, recovering the membrane's performance. Now, look at the lead elements of a seawater system operating at 70 bar with the exact same water. The extreme forward thrust changes the physics of impact. Particles violently deform, crushing together and embedding deep into the pores of the thin film layer. This mechanism is called inelastic cake compaction. It is a state of irreversible particulate fouling. Because the compacted layer loses all porosity, it acts like a concrete wall. Chemical recovery becomes physically impossible. The chemicals cannot penetrate the dense layer, and the membrane is permanently blinded. Irreversible flow reduction is the first symptom in a seawater system, but the secondary consequence is a fast-moving mechanical failure cascade. In this 3D wireframe, inelastic compaction blocks the feed channel spacers, creating a bottleneck that triggers a rapid spike in flow resistance. When differential pressure crosses 1.5 bar per element, the restriction generates immense forward-pushing hydraulic force. The extreme pressure extrudes the membrane. The leaves slide forcefully forward along the central permeate tube, expanding outward and shearing against their own structural supports. Engineers refer to this specific structural destruction as the telescoping effect. Once the element telescopes, secondary damage follows immediately. Anti-telescoping devices fracture, rubber O-rings fail, and brine seals tear open. Salty feed water bypasses the membrane completely, causing an instant spike in permeate TDS. In high-pressure environments, a high silt density index represents a structural shear force threat that quickly moves beyond the scope of simple chemical fouling. Because seawater fouling is irreversible, controlling the SDI cannot be a reactive process. It requires a sequentially engineered multi-barrier defense upstream. The The first line of defense is the high-rate solid contact clarifier, or HRSCC. Operating the clarifier requires strict optimization of coagulant mixing speeds to build heavy flocks. You must also manage bottom blowdowns aggressively to ensure the sludge blanket never rises high enough to overflow into the downstream process. Water then flows to the multimedia filters, which are designed to catch the fine suspended solids that escape the clarifier. This diagram illustrates the primary failure mode of a multimedia filter: media channeling. A void forms, allowing water and colloidal particles to bypass the media entirely. Because water flows freely, the pressure drop remains deceptively low, even while SDI spikes downstream. Upstream physical bypasses, whether from a clarifier overflow or a channeled media filter, mathematically guarantee the destruction of the downstream reverse osmosis membranes. Ultrafiltration acts as the primary submicron barrier. Its precise engineering ensures the feed SDI remains permanently below 3. To keep the ultrafiltration pores open and maintain a stable transmembrane pressure, operators execute daily chemically enhanced backwashes. If the SDI exceeds 3 despite these backwashes, operators execute a membrane integrity test. This protocol uses compressed air to precisely locate broken hollow fibers that fail to hold pressure so they can be isolated. The water then passes through a 5-micron cartridge filter. This is strictly a final safety buffer. It is not an active SDI control device. Cartridges are replaced based exclusively on a differential pressure limit of 0.8 to 1.0 kilograms per square centimeter. Properly seated O-rings within the housing are critical here to prevent any last-minute bypass. Ultrafiltration integrity and secure cartridge housing seals are the absolute last chances to intercept suspended solids. Once water passes this point, it hits the high-pressure pump. This dashboard synthesizes pretreatment data into 3 standard operating zones based on the measured silt density index: Zone 1 under an SDI of 3, Zone 2 between 3 and 5, and Zone 3 above 5. In Zone 2, a brackish water plant enters a warning state. Operators must optimize coagulation, increase multimedia filter backwash frequencies, and prepare for an early cleaning in place. Standard triggers for a brackish water CIP are clear. Initiate cleaning when the normalized permeate flow drops by 10 to 15%, or when differential pressure rises by 20%. The protocol utilizes 2 targeted washes to recover performance. An alkaline wash at a pH of 11 to 12 removes organics and silt, while an acidic wash at a pH of 2 targets inorganic scaling. That chemical recovery is standard for brackish water, but for a seawater system entering Zone 3 with an SDI above 5 requires an instant emergency plant stop. Running a seawater high-pressure pump with an SDI above 5 mathematically guarantees inelastic compaction and the subsequent telescoping of the elements. The Silt Density Index tells you the volume of foulants entering your system, but thermodynamics strictly dictates the ultimate penalty. In high-pressure environments, you simply cannot clean your way out of poor